So in the last video, I went over the no calculator part of the chapter 1 and 2 exam. So in this one, we'll talk about the calculator part. So the very first problem was going over the topic of attending to Christmas. And the problem was that I rolled a bowling ball down a 60-foot lane. And I wanted to know my velocity when the ball hit the pin. Okay, the very first thing you're supposed to do is graph your data and that's it. And this was your data given. So we're given the time and distance. We're given 5 points. Okay, so at 0 seconds, you're at 2.3 seconds, you're at 5.2 feet. At 4.7 seconds, you were at 22 feet. At 7.3 seconds, you were at 53.4 feet. And then you don't know what time you hit the you hit the pins at 60 feet. So the very first thing you were supposed to do was to graph this data and then use your graph to find the time at moment of impact. So if you graph your data, you notice it looks like a parabola. And then when you do your line of best fit, so you have a parabola. Okay. So this is what your line of best fit looks like going through your point. Then you were supposed to use that line of best fit to see what time it was at the moment of impact here at 60. So according to this graph, my time of moment of impact is about 7.7 seconds. Okay, so you know at 60 feet, your time was approximately 7.7 seconds at moment of impact. Now that you have that information, this then asks you to graph your data by hand. So you had a graph of your time in seconds versus your distance in feet. And you went up to 1, 2, 3, 4, 5, 6, 7, 8 seconds. And you went up to 60 feet. And you could graph all your data. So at 0, you were at 0 feet. At 2.3 seconds, you were at 5.3 feet. At 4.7 seconds, you were at 22 feet. At 7.3 seconds, you were at 53.4. And then at 7.6 seconds, you were at 6. So you kind of have this parabola right here. Okay? Then you were supposed to draw a line through, a secant line through 2 points on your graph. The problem said one of your points should be the moment of impact, which as we know is at 7.7 seconds and 60 feet. The most obvious choice for the other point is the one closest to your moment of impact because that's the most accurate secant line. So we're going to choose our other point to be here at 7.354. So here's your secant line. Okay. Then you had to use that secant line to find your approximate velocity at your time of impact. So that was letter C. Your approximate velocity is the slope of your secant line. which is your change in y over your change in x. Your change in y is 60 feet minus 54 feet. And your change in time is 7.7 seconds minus 7.3 seconds. Okay, if you plug that into your calculator, you should have gotten 7.3. About essentially 15 feet per second. The problem asked for feet per hour, so you had to convert this 15 feet per second times 60 seconds per 1 minute times 60 minutes per 1 hour, which leads to 54,000 feet per hour. Some of you converted this into miles per hour, which was fine, but I wanted to at least see feet per hour. Okay, so that was the first calculator problem. The second calculator problem was asking you to look at the linearization of y equals n. So that was looking at explaining and justifying. And we did this problem in class. I'll go over it now. So first you were supposed to complete this table for two functions. The first function was for y equals sine of x. And the other function was the straight line y. You were given different x values to evaluate the function. We were given -1, negative 0.1, negative 0.01, 0, positive 0.01, positive 0.1, and then positive 1. If you were to plug -1 into sine of x, you would get approximately negative 0.3. If you were to plug -0.1 into sine of x, you get approximately -0.1. And then so on and so forth. So we're supposed to get all these y values for your x. Obviously, for the line y equals x, your y is equal to your x. So these were your values. Now, if you notice, okay, your line y equals x starts looking like y equals sine of x. So y equals x looks like y equals sine of x for x values close to 0. So obviously here at -1 and 1, your values aren't really the same. But as you get closer and closer to 0, your y values start being the same for the two functions. Then you were asked, so the x values of negative 0.1, negative 0.01, 0, 0.01, and 0.1. Okay, then you were asked for which values y equals x is an over approximation. So what you get for y equals x is larger than what you would get for sine of x. So greater than. Clearly, it's greater than sine of x here. And it's actually greater than sine of x here and here. So y of x is an over approximation at x greater than or greater than 0. When y equals x is an under approximation at, so as you can see, y equals x is clearly smaller. It's a bigger negative number than the one for sine of x. Many of you confuse this. -1 is smaller than negative 0.84. It's a bigger negative, so it's smaller. So y equals x is actually an under approximation for values less 0. Okay? And you can actually see this on the graph. So I'll show you if we graph y equals x and y equals sine of x. Oops. Sine of x. Okay. So as you can see, I have the line y equals x. So as you can see by the graph of y equals x and y equals sine of x, for values of x less than 0, y equals x is an under approximation of y equals sine of x, literally under the graph. And then for values of x greater than 0, y equals x is an over approximation for the graph y equals sine of x. And as you get closer and closer to 0, they start looking the same. So then the last question asks you to estimate the limit as x approaches 0 of sine of x over x, and you had to justify your answer. So as x got closer to 0, sine of x started looking more like y equals x. So as x approaches 0, sine of x over x looks more like x over x, because sine of x looks more like x as we get closer to 0. So the limit as x approaches 0 of sine of x over x starts looking like the limit as x approaches 0 of x over x, which happens to be the limit as x approaches 0 of 1, because x divided by x is 1. The limit of 1 as x approaches 0 is just 1. So the limit as x approaches 0 of sine of x over x is equal to 1. So using our graph, our data, we saw that sine of x started looking more like x as x approached 0. So as x approaches 0, this limit starts looking like the limit as x approaches 0 of x over x, which is just equal to 1. Therefore, the limit as x approaches 0 of sine over x equals 1. If this is confusing to you, you have no idea of anything I just said, you should come in or spend some more time thinking about it and working it out. But that was the last problem on the calculator section. In the next video, I'll review more secant and tangent lines and how they lead to the definition of the derivative.